Well, here is an unbalanced redox equation, and our goal is to balance this using the half equation method. So there are 4 steps involved in balancing this redox equation. Step 1, we have to identify the species that are oxidized and reduced. So let's determine the oxidation state of manganese here. So that is +7, because this is, let's say, X unknown, and oxidation state of 4 oxygens, that's -8. So the net oxidation state on this ion is -1. So the manganese oxidation state here is +7, X is +7. And if you look at this one, the oxidation state of manganese on this side is +2. So the net change in the oxidation state of manganese is a decrease. And let's do the same thing for iodide ion. So we have iodide ion, I-, whose oxidation state is -1, and here we have iodine molecule whose oxidation state is 0. It's a neutral molecule. So this is an increase from -1 to 0. That's an increase. So we can call that as oxidation, whereas manganese is oxidation state is changing from +7 to +2, so that's reduction. So for manganese that would be reduction. So we have identified the species that are being oxidized and reduced. Now let's write the oxidation and reduction half equations. So my oxidation half equation would be this one, I- is converted to I2, and my reduction half equation is, let's call that reduction half equation. My reduction half equation is MnO4- is being converted to, let's call that as Mn2+. That's Mn2+. So we've written the oxidation and reduction half equations, and but we are still not done yet. We have to balance these 2 half equations. So we have balanced the atoms, balanced the electrons, all of that. So I have 2 moles of iodine here, so I have only 1 mole, so I make this 2, right? And then we said oxidation, so electrons are being lost. So oxidation state of iodide ion is changing from -1 to 0. That means there is a net loss of an electron per iodide ion. So each iodide ion, for example, I- to I, that's a net loss of 1 electron. Since we have 2 moles of iodide ions, so the net loss of electrons would be 2 moles. So we have balanced the atoms of iodine. We also have balanced the electrons here. Let's do the same thing for MnO4-. So the number of manganese atoms are equal on both sides, but the oxygens are not balanced. So when you want to balance oxygens in a redox equation, we use water molecules to balance. So to balance 4 oxygens, I need 4 water molecules, right? So by adding 4 water molecules, now our hydrogens are unbalanced. So I have 8 moles of hydrogen ions on the right, and I have none here. So I will simply add 8 moles of hydrogen ions to balance the hydrogens, right? So our oxygens are balanced, our hydrogens are balanced. But what about the electrons? So the net oxidation state change, the net change in the oxidation state is from +7 to +2. So that means there's a reduction by factor of 5. That means this manganese ion must have gained 5 moles of electrons to reduce from +7 to +2 state, right? So now we have balanced the atoms, the electrons in the individual half equations. But in the next step, we're going to add these half equations. But before we do that, we have to make sure the electrons are equal in both of these half equations. So I have 2 moles of electrons here, I have 5 moles of electrons here. So we have to make sure that the number of moles of electrons in both the half equations are equal. So one way to make these electrons equal is by multiplying this entire equation by 5, so that becomes 10 moles of electrons, and I can multiply this entire equation by 2, so that becomes 10 moles of electrons as well. So let's rewrite the equations how they look like after we multiply them. So in step 3, that would be my oxidation half equation would be 10 moles of iodide ions, that's 5 times 2, and 5 moles of iodide would give me 10 moles of electrons. Similarly, my reduction half equation would be, that's 2 times MnO4 minus, that's 2 MnO4 minus plus 16H plus 10 moles of electrons would give me 2 Mn2 plus 8 moles of water. So now we have equal number of moles of electrons in either side. So in step 4, what you got to do is simply add these two half equations. So when you're adding step 4, we simply add these two half equations. So when you add them, you can see that we have 10 moles of electrons on the opposite side, so we can cancel these out. They cancel out. And whatever atoms are remaining, we simply add them together. So on the left hand side, I have 10 moles of iodide ion plus 2 moles of permanganate ions plus 16 moles of H plus. And on the right hand side, well, we cancelled out the electrons, but we are left with 5 moles of iodine molecules, 5 moles of iodine, 2 moles of manganese 2 plus ions, and 8 moles of water, right? So this is our balanced redox equation. Well, we have already balanced the charge by making sure the number of moles of electrons are equal on either side. But if you want to do a quick check if the atoms are equal, so I have 10 moles of iodine there, I have 10 moles of iodine atoms, I have 2 moles of manganese there, and I have 2 moles of manganese, I have 8 moles of oxygen, and I have 8 moles of oxygen. So let me write that down. So I have 10 moles of iodine here, I have 2 moles of manganese, and you have 2 moles of manganese, they're equal. I have 8 moles of oxygen, I have 8 moles of oxygen, and I have 16 moles of hydrogen. I have, that's 8 times 2, I have 16 moles of hydrogen ions. And we have 10 moles of iodine here as well. So if you compare the number of atoms or ions, they're equal. So 10 moles of iodine atoms, 10 moles of iodine atoms, 2 moles of manganese, 2 moles of manganese, 8 moles of oxygen atoms, 8 moles of oxygen atoms, 16 moles of hydrogen, and 16 moles of hydrogen ions. So this equation, this redox equation, is said to be balanced. So that's a balanced redox equation.